advisor, Emma and Reluka. So first, I want to begin by telling you a story about Bob here. So Bob here is using end-to-end encrypted messaging, and like Bob's really happy because end-to-end encrypted messaging gives you really nice guarantees. The server that is providing the service can't really read Bob's messages. Bob is pleased. Now, life happens, and let's say that Bob breaks his phone. Now the secret key that Bob uses to decrypt his messages is gone, and Bob is displeased. I tell you this story because I was actually Bob last year. I went skiing last spring. I wiped out, and then my phone fell into the snow, and I could not find it. It's still in Lake Tahoe somewhere. So this is me messaging Rolf saying, hey, I lost my phone when I went skiing yesterday. Did I use SVR? So let's get back to thinking about how we actually back up secret keys. So the obvious straw man solution that you could do is to just give your key over to Signal and say, hey, store this for me. The problem here is that now Signal has your key and can decrypt your messages, and that really undermines all of the nice privacy and security guarantees that you get from using end-to-end encrypted messaging. So there's a couple other ways you could back up your secret key. If you've ever used any sort of security service, they might make you print out a bunch of random looking strings and say this is your backup key, stored in a safe somewhere so that you can always access it. That's not very user friendly. In fact, I don't think I've ever been able to store a paper key reliably for many, many years. So one solution that we have in the usable security space is to use a low entropy pin to derive your secret key. So you can think of mashing in together this pin that's 4 digits long when you are calling your key derivation function. You can think of it that way. In case you've ever used Signal Messenger before, it always has that pop-up that's hey, verify your security pin so that you know it. The reason it asks you this so many times is that if you don't remember your pin, you can't recover your key. So the problem here is that the pin can be brute force, right? If you're using a 4-digit pin, that's 10,000 guesses before, at most 10,000 guesses before you get your key. And what you could do is limit your guesses with secure hardware. And the problem here is that if you use a single type of secure hardware, that there are always exploits or attacks that are being waged on secure hardware. You read about these. So a single type of secure hardware can be compromised. So what we do instead is we use this low entropy pin to, instead of derive the secret key, we'll derive shares of a secret key with some enforced guess limit. And the motivation here is that if you're using heterogeneous secure hardware, so different types of secure hardware to hold each share of your key, it's pretty unlikely that all of them are going to be compromised at once before you say reshare your key. So now Bob is pretty happy because no single trust domain can compromise secret key. These are actually masked shares, but there's a link to the paper at the end if you want to read about the cryptographic protocol we use to make this happen. This talk is more about how we actually build the system to sort of realize this setup. So SVR3 is, at least to our knowledge, the first cross-enclave, cross-cloud system. And this means that these trust domains are actually running, each trust domain is a cluster running a certain type of secure hardware. And we defend against internal and external attackers, which I will give you more slides about in a couple slides. And the capacity, we have capacity for doing key recovery for 500 million users at fractions of a penny per user per year. So for the roadmap of this talk, I first will talk to you about the layered security guarantees, and that's just sort of to give you an idea of what attackers we're trying to defend against. Then I'll talk about how we build the SVR3 backend, and I'll give you some evaluation numbers. So first, layered security guarantees. I've been saying the word trust domain a lot, and I want to define a trust domain as something that is a replicated enclave cluster that's running on a single type of secure hardware on a single cloud provider. So for example, this is a cluster of Intel SGX enclaves that are running on Microsoft Azure. So different trust domains means that we're using different types of secure hardware in each trust domain, and we're running it on different types of clouds. So in our deployment, the other ones we're using are AWS Nitro and AMD SEV-SMP on Google GCP. So what type of attackers are we concerned about? We break these down into primarily two types of attackers. The first one is actually Signal itself. So Signal is, we store there's a lot of like sensitive information that's going through Signal. And that means it's actually quite like a juicy target, right? So it would be really nice if you can actually build a system where you assume that your system administrators can be malicious. Like they could be compromised and they could deploy a malicious service that, say, tries to dump all of the secret keys that are being backed up. So this is what we call the type 1 attacker. This type 1 attacker, if we assume that they're like a system administrator, can compromise the deployment. They can spin up and spin down cloud machines. They can deploy malicious code on servers. And they have no physical access to cloud machines, but say like they have pseudo access. So the second type of attacker that we also want to consider is the cloud provider themselves. So this is what we call our type 2 attacker. And this is, an attacker that can access the hardware. They have physical access to the deployment. So you could run things like, say, like DIM interposer attacks if you have access to the server. And I'll be talking about this a lot more later, but if you have physical access to a server, you can run these things called rollback attacks, in which you can continuously like reset server state to some previous point in time. And I'll have slides on this later, but you can already sort of think about how that's bad for a system where we want to limit the number of guesses for a PIN, for a user's PIN. The type 3 attacker you can think of as just like some hacker. They could turn into like a type 1 or a type 2 attacker, say if they like phish a Signal employee or gain access to a data center. So the security guarantees that our system provides is that when we deploy it on n trust domains with m replicas per trust domain, and we have these parameters T and S, SVR3 can, without letting an attacker compromise the user's secret keys, tolerate total compromise of at most T trust domains. So that's what we call security across trust domains. And we sort of get this intuitively by splitting up the key into multiple shares. So you have to have you need a threshold number of shares to reconstruct the key. And we also can tolerate software rollback attacks, and at most S physical rollback attacks inside each trust domain before that trust domain is considered fully compromised. So this is sort of security within a trust domain. Although we can tolerate a trust domain totally being compromised, we are trying to also make it harder to compromise a given trust domain. So in the deployment that we have, here n is 3, Azure, Google, and AWS. M is 7, so we're running like clusters of 7 servers on each cloud. And then T is 2, so you could compromise at most 2 of each cloud provider. And S is 2, so within like a cloud, you can go and physically roll back 2 of the machines in the cluster. So here is where I give a statement about availability that may be kind of controversial to systems practitioners. So we provide availability when T+1 trust domains are operating correctly. And we define this as enclaves in the trust domain being online and like none of the enclaves being under attack. This is what you can think of as normal operation. Like no one is attacking the system, we are available. When we are under attack, we actually prioritize safety over availability because we would rather have a user's secret key not be compromised versus providing the service at all. That's the threat model, or that's like that's the model that we are operating under. So now I'll talk about how we build a SVR3 backend. So the enclave model that I have for you is we assume we're running enclaves that provide a couple of guarantees. One is application level attestation. This means that if I am a client, I can verify with the enclave that a certain code is running, like a certain application, fixed at like some version, is running on that enclave. We have memory access control, which means that when I'm running inside this enclave, like an outsider, usually like the memory is encrypted, so the outsider cannot just dump like the memory of this application and get the shares that way. And that the attacker has page level rollback granularity. So if an enclave type will lose any of these guarantees, then we consider the trust domain to be compromised. But again, like I said before, we're still protecting user secrets when at most T of these trust domains are compromised. So rollback attacks. Enclaves are susceptible to software and physical rollback attacks. You can think of software as like the type 1 attack. You know, the system administrator can turn the service off, maybe like try to roll it back to a previous state and then like reboot the service. And then a type 2 attack is like you're running like a DIM interposer. You can do rollback attacks on the memory contents, even if they are encrypted. So rollback attacks undermine guess limits because if you have rollback attacks, the attacker can trivially get more pin guesses. So to just like illustrate this for you, let's say your guess count for this user's pin is 2. The attacker makes a pin guess count increases to 3. You roll back the server, the guess count goes back to 2, the attacker can make another guess, and the guess count goes back to 3, even though you made 2 guesses. So software rollback attacks this is something you have to sort of understand about how these enclaves work. If you store external state outside of the enclave via something called data sealing, you can roll this back because you can just swap out the external state with an older version and then reboot the enclave, and boom, you roll back your enclave. So we actually protect against this by just trivially not using this feature. We just store the entire database in memory of user key shares. And if you're not storing external state, you can't roll back any external state. Now the problem here is that, wow, if one of your machines falls over, you're going to lose all of its state, and that's not great for operating any kind of service. It's not very reliable. So what we do is we replicate across a cluster of enclaves, and we use Raft like inside each trust domain. So yeah, that's why trust domain like logically looks like one server, but it's actually like a Raft cluster. And I say Raft, but vanilla Raft also has problems. So do people know what Raft is, or like fault tolerance protocols? Okay, I guess half of this room. It's good. So it's a crash fault tolerance protocol, which means it provides safety and liveness in the event of server crashes, but not necessarily when the server is like not following the protocol. So to give like a quick refresher on Raft, like you have an elected leader basically that appends to the log and propagates to followers. As a thought exercise, what happens if we roll this leader back? I can let you think about that for like a couple seconds. The answer is not good things. You can, just by like rolling back one server, which happens to be the leader, you can arbitrarily roll back guess counts. So hardware rollback attacks, like I said before, are when you roll back internal memory during execution by interposing on the system bus. Vanilla Raft is a crash fault tolerant protocol, and it loses safety guarantees when this becomes like a part of your like operational model for the server. Like if the server can be arbitrarily rolled back, vanilla Raft is not safe, because if you roll back the leader, you can basically equivocate on the log. An observation we make here is that physical rollback attacks, they're harder to carry out, and it's harder to compromise the trust domain if we say protect against some number of physical rollback attacks in its cluster. So we actually modify Raft to make it rollback resistant. So we call this rollback resistant Raft. Rolf said I should put this here. So it's a rollback resistant consensus protocol. We have a lot more details in the paper, but we make 3 main changes. The first one is that when we're processing append entries requests, we do this hash chain verification. And then we also require supermajority so that the quorum intersection always includes at least one non-rollback server. And then we have a promise round before the leader proceeds with the update. We take these changes, So for safety, the informal safety theorem I have is that for every log entry that's been applied to the state machine for some server, if the number of physically rolled back servers is less than or equal to S, then server I is never going to apply a different log entry at that log entry's position. So that's just to say, if you commit a guess and you have not rolled back more than S servers, you're never going to roll back a commitment to that guess. For safety, we require M greater than S replicas, but S may be set smaller depending on how many crash failures you want to tolerate. Our paper proves the safety of our modified Raft protocol and also gives the TLA plus specification of the modified Raft protocol. For liveness, like I said before, it's not really a goal for SVR3 when the cluster is under physical attack, but when you're operating normally, we just require you to have m-s/2 crash failures to be live under normal connectivity conditions. So again, in our deployment, that's, we have 7 replicas running. We can tolerate 2 crashes and still have liveness if the system is not under attack. So now I'll just give you some evaluation numbers. 3 enclave types and clouds: Azure Scalable HDX, GCP AMD SEV SMP, AWS Nitro. We provision, key recovery is not a super frequent event. I'm not losing my phone every day. I lost it once last year. So we provision for 1 request per second per million users and about 256 bytes of RAM per user because the shares are actually quite, compact. The deployment supports 500 million users at, fractions of a penny per user per year. The evaluation numbers I'll give you are on a staging cluster that's provisioned for 10 million users. So end-to-end performance, we see 365 milliseconds for doing both a store and a recover key. The average throughput is about 1,000 requests per second, which if you're looking at our throughput goals, exceeds it. I know these are insane numbers for a systems audience, but this is what happens when you work at the intersection of systems and security. If you just want to know where the time is going, you see about 30% is going to attestation. A pretty trivial amount is going to the actual crypto, and then most of it is going to waiting for the servers to acknowledge your request or your guest count. Yeah. Okay. Now some fun takeaways, also known as my soapbox. I think there's from working on this project, there's 3 takeaways that I walked away with. The first one is that security guarantees of mainstream cloud providers are a moving target. I abstracted a lot of this away in my talk, but a lot of time was spent on actually figuring out what sort of security guarantees these hardware enclaves that are being provided by cloud providers actually give you. To give you an example, Intel HDX, the first version had a Merkle tree over the memory, which means that you had both you had integrity over the memory and freshness protection. So you couldn't just roll back arbitrary pages because if you did that, then the Merkle tree hash would not match. They actually removed this in Scalable HDX, and there's no document or change list that's saying this really convenient security feature is now gone. That's also why it's Scalable HDX, because you're no longer computing this.
It's not a bug, it's a feature.
Yeah, exactly. So it's really a moving target. A lot of work was done in just actually unifying the state of the world for enclaves at this point in time when we were building the system. The second one is that proving safety helps find bugs. When we were writing the safety proof for our modified RAF protocol, we found bugs, and that made us modify our RAF protocol further. So I think, it's a pain. It's also requires quite a bit of rigor, but it matters. The third one is that pins are scary, and that is actually, I'll just leave it at that. Pins are scary. We had to really build a lot of infrastructure. This is a lot of thought to make this security feature, which looks nice to users, actually secure. Okay, cool. So in conclusion, SVR3 enables secret key recovery and protects against internal and external attackers by distributing trust across heterogeneous secure hardware. There's a QR code for the full paper. We have a GitHub repo if you want to look at the implementation or look at the TLA Plus specification. And yeah, thanks. I'm happy to take questions. Yeah.
So for each of the split secrets, is it one split on only one single cloud provider? Oh, sorry. Also, Vivian, please repeat the question for the recording.
Yes, for the stream.
Sorry, I'll repeat. My question was, for the split secrets that are shared among the cloud providers, does only one cloud provider only have one part of the secrets? What I'm saying is is one part of the secret are they on 2 cloud providers? Like in the image you showed, it's like 1 for cloud providers.
Yeah, so the question is, how many shares is each cloud provider storing? The answer is 1. So this is like, we're doing like 3 of 3 secret sharing. Each cloud provider gets 1 share of the secret. And that does mean that you need all 3 of the cloud providers to return that share to you for you to reconstruct your key.
So what, I guess my follow-up to that is, what happens if like one day it's like, oh, AWS or Azure just goes down and it sucks, and now what?
Yeah, so the question is, okay, then if one of the cloud providers goes down, you are losing, availability. Your user can no longer recover their keys. Yeah, so if there's an outage, you cannot recover your key that day for this, for the current parameters that we set. This is like a trade-off. Like you could say, let's make it 2 out of 3 secret sharing so that we can tolerate the loss of, one of the shares. Yeah, so.
So why do you not do that? Sorry.
I think so the trade-off is that you can tolerate the loss of a share, but now you can compromise a user secret if you can compromise more than 2 of the trust domains. Yeah, so it's kind of like a parameterized thing. Like you can take more availability over less security. I think Signal just the I guess the consideration is always erring on the side of more security for the user.
Thanks for the talk. Do you have any thoughts about whether this approach will hold up in a post-quantum world?
Yes. So the question is, what about post-quantum world? So what you have to do is basically upgrade the secret sharing that we're using to split the shares across the clouds. So in right now, the protocol or the secret sharing, the PPSS protocol that we use is not post-quantum secure, but there are some things that you can do to make it post-quantum secure. Yeah. Good question.
Hi, really good talk. I'm wondering what is the decision or any trade-off that you do when you decide to do a custom graph versus just using the BFT protocol?
Yeah, so the question, that's a good question, is what trade-off do you consider when you are, modifying, rolling a modified version of RAF versus just any BFT protocol? The answer is that I think it's quite interesting because in the enclave model, you're not, the behavior is not necessarily arbitrarily malicious, it's just that you have rollbacks, right? But you're rolling back and you will execute the protocol. And that means you can make a little bit more of a performance gain because if you're using a traditional BFT protocol, you're doing like N of N broadcasting, and we can avoid that by modifying RAF.
Sure.
Yeah, really cool talk. I don't use Signal, so maybe this is kind of obvious, but as a user Signal, is there a way to know that Signal's actually doing this? Or is it possible that they say they're doing this, but they just store it on their server?
Yeah, so that's the question is, how do we know that Signal's actually doing this? So when the Signal clients are actually shipped with hashes that you expect for what the server is running. So the client itself does run this remote attestation process with the server. So that's how you verify that the server is in fact running this. And then all the code is open source. You can reproduce the build, and you can audit it. Yeah.
So Raft is definitely a better thing to do than Paxos, right? But I'm really curious, did you try and just test for what happens in terms of partition tolerance? Did you do any Jepson testing against this to see what happens when you get into a split, right?
I see. I think, so the question is, do we do like empirical testing for if we have like partitions in like the cluster? The answer is no, but I think like the safety proof is kind of like, under the specification of the protocol, you should never end up in a state in which after you have like gotten, this number of acts back from replicas that you end up having a split brain, like, because, and like it really boils down to the fact that like you should have had enough acts such that like when you intersect like the number of like replicas that have a different state versus the one that has like the committed state, you should always end up at least like one voting node that has the correct state and is not going to vote for the
Right. I think the beautiful word you use there is should, right? So that's why you do a Jetson test to actually prove that you actually get that state, right?
I see. So I think so I guess testing this is a bit hard. Like what I can do is like, I can take the TLA plus specification, I can run the model tracker, and I can say it ran for like 48 hours and like nothing's happened. But and we did do that. Like we did run it for 48 hours, nothing happened. But it's like we can't really make guarantees beyond that, right? I suppose we could run it for longer, but that is one thing I would really like. Doing like these manual proofs is very hard. If we could do this automatically, it would be great.
Thanks very much. Great talk, by the way.
Thanks.
I think we're going to move on to the next talk. So thank you so much.